He has been at the forefront of introducing modern data science approaches to oncology research and clinical care, leading multiple clinical trials for both rare and common kidney cancers. What makes Dr. Msaouel's work truly unique is the way he bridges medicine and statistics. His contributions span both theoretical and applied fronts, from advancing statistical methodology in journals like Biometrics, Statistics in Medicine, and Harvard Data Science Review, to developing data science frameworks that have positioned MD Anderson as the global hub for renal medullary carcinoma research, and his innovations such as reframing the bias variance trade-off into the relevance robustness trade-off and applying structural causal modeling to oncology are reshaping how we think about trial design and personalized decision-making in rare diseases. We are honored to have him share his insights with us today, especially the interaction between statistics and medicine. And before we begin, just a quick reminder, today's webinar will last about 1 hour. Time for questions, and at the end, please type your questions into the chat box and we will address them during the discussion. So the session is being recorded and will be made available to ISBS members afterward. So without further ado, let's welcome Dr. Msaouel. So Pavlos, the floor is all yours.
Thank you all for the kind invitation and for having me and for the opportunity to discuss about randomization in clinical trials, its pros and cons, and potential pitfalls, particularly in relation to biopharmaceutical statistics. These are my disclosures. None are directly related to today's talk, other than the fact that I do run investigator-initiated clinical trials for rare and common kidney cancers with the companies here. Some of their products may be discussed today, but in a completely different context. So I take care of kidney cancer. That's all I do in clinic, including today. And our clinic is a little bit unique in the sense that we specialize in the rare and the difficult kidney cancers. So there are other clinics that are dedicated exclusively to kidney cancer, but they typically see more of the most common type, which is what we call clear cell kidney cancer, which is about 75% of cases. And then there is the other 25% that is what we call the non-clear cell kidney cancers. And that is divided into many different subtypes. So my clinic actually sees more of the non-clear cell kidney cancers than the clear cell. We're that specialized. We like the really difficult cases like this ones. And we have a particular interest in this one, renal medullary carcinoma, abbreviated as RMC. A very rare and super deadly kidney cancer. Since I specialize in kidney cancer, that's all I see in clinic. I can tell you with confidence, it is the deadliest kidney cancer of adults easily if it is not treated appropriately. And my lab, I have both a wet lab that does animal experiments and cell line experiments and other modeling, etc., and a dry lab effort and design and run clinical trials for renal medullary carcinoma, abbreviated as RMC. And when we were first embarking on our efforts to do research for this kidney cancer, I was being advised that this is the equivalent of career suicide. And now people say, oh, you know, you have created this infrastructure and it's great and all of these things. We've got all this funding. We've got all these trials. You got set up because of X, Y, and Z. They find excuses of why we succeeded. But the honest answer is it took a lot of grit, a lot of effort. And we needed to understand why people were telling us that it's impossible to do research for RMC. Why is it a career suicide? And one of the things that people were telling us, not at MD Anderson, thankfully, is that you cannot do randomized trials for RMC because it's so super rare. And since you cannot do standard randomized trials, you cannot move the field forward, and you certainly cannot advance, my career. So just for context again, RMC, extremely aggressive. Another reason why people are so scared of it is because it is the only cancer that I'm aware of that so specifically afflicts a minority, young Blacks, African Americans in the United States, because of its connection with a blood disorder known as the sickle cell trait or other sickle hemoglobinopathies. It's so deadly because it is defined by the loss of one of the most powerful tumor suppressors in oncology, SMARCB1. It's very rare that cells can lose SMARCB1, but when they do lose it, they become beasts. Very, very difficult to treat. The therapies developed for the most common kidney cancer, clear cell kidney cancer, are completely ineffective against RMC. So the FDA-approved therapies for kidney cancer don't work against this one. The immune checkpoint therapies that many of you know have transformed oncology care are also completely ineffective. In fact, and I'm not going to talk about this today, they may make RMC cells grow faster. That's how tough of a disease this is. And interestingly enough, the regimens, old school regimens that do not work against most other kidney cancers, can occasionally work against RMC with a response rate in about 1/3 of patients, but those responses are very, very brief. And to make a difference, given how challenging this cancer was, we established the global hub of RMC research in our group. I literally manage more than 60% of these cases globally. Most of them cannot come at MD Anderson, so I help clinicians from all over the world from afar 24/7. Literally, as I've been talking to you guys, I literally received an email from somebody asking me about RMC. Earlier in the morning, I got another one from South America. For context, some of you may have heard about the SEER database, which in December 2023, these are published data, reported on 100 patients with RMC. At MD Anderson, in a similar time frame, we have 135 patients with RMC. And keep in mind, the ones at MD Anderson are have a lot of granular details. They're definitely correctly diagnosed. We have molecular sequencing. We have very, very reliable demographics, et cetera. And that helped us being able to make a difference for this cancer. For context, when this cancer was first described in 1995, the median survival, there is no stage 1, stage 2, whatnot, it's all essentially stage 4, was 4 months from diagnosis. And again, most of these patients are otherwise healthy and in their 20s. And imagine telling somebody, you've got 4 to 12 months to live. By 2017, despite all of the progress in oncology at that point, the median survival was still just 13 months. So about half of these patients would die within a year from diagnosis. So we set up very clear benchmarks and we're very transparently, this is on, you can find it easily on this link. We said we're going to get the median survival to 2 years by the end of 2025. And we have largely achieved that goal. And we're going to, as you can see here, and you can see this again is published data, the acceleration in 2 years survival probability, here just by diffusion, just by improvements in accurate diagnosis, et cetera, there was some improvement, but you see here this acceleration. This is essentially us bringing to 2023 what would probably have happened by 2030. And that happened because in 2017, the first ever funding ever for this kidney cancer was allocated by the American Society for Clinical Oncology, ASCO, as a Young Investigator Award to me. I was a fellow at the time under the mentorship of Nizar Tanir. And with that seed funding, we did biological research that allowed us to open the first 3 investigator-initiated clinical trials just for this kidney cancer. They were not randomized clinical trials. And through a very disciplined data science and trial infrastructure and framework, we turned the knowledge from these trials into improvement for these patients. Whether these trials are negative or positive, we move forward. In fact, every time those trials are so-called negative, we learn more. Why? Because literally the definition, as some of you may know, I'm sure, the definition of information is surprise. And so when your hypothesis is refuted, that surprise is information. And now we have another ongoing clinical trial for this kidney cancer and another cancer now expanding to another rare tumor that is SMARCB1 negative, driven by the same tumor suppressor known as epithelioid sarcoma. That's the other cancer ongoing at MD Anderson. A fifth clinical trial will open in 2026. For context, there is no other rare kidney cancer in the range of 5%. Remember, this one is less than 1%, in the range of 5% or less that has a single dedicated clinical trial. Some of them may have one or two, but definitely not 4 or 5 now, and hopefully soon even 6 clinical trials. How are we doing this? Through biological insights that and rigorous data science principles that guide the therapy development. And that's what I'm going to talk to you about today. I'm going to focus on the data science aspect, which I think is important for you guys. I can talk about RMC all week, but I think data science will be very valuable. What did we learn? How did we attack this cancer and others to accelerate our inferences and our knowledge? So the first thing that we thought of when we were embarking on our mission to help patients with RMC is what we call the first law of data analysis. This is something that Ken Rothman, some of you may know, at the University of Boston, he asks of graduate level statisticians, he does this test, he asks this exact question. There is no catch. This is a question that applies to just about every scenario when it comes to statistical inferences. As the number of patients enrolled in a clinical trial increases, the probability that the uncertainty, the standard error, or a function of the standard error, like a confidence intervals of the trial's results, and it doesn't need to be a trial. It can be any experiment. It can be any statistical inference, includes the truth. 1 increases, 2 decreases, 3 remains the same, 4, I have no idea. Most people, when we asked, including faculty and fellows, including at MD Anderson, say increases, some say decreases, some say remain the same, very few say I have no idea. You guys are experienced statisticians, so I believe many of you know that the answer is decreases. Interestingly enough, you know, this is something we've been talking about for more than half a century. Nowadays, with the big data and the LLMs, there is some debates even about whether this law always applies. I have a link here. You can read more about some of these very, very interesting considerations. For the purposes of today's talk, we will assume it applies to everything because it likely is, at least for clinical trial inferences, which is our focus for today. Why? Why does it decrease? Because of the very well-known bias variance trade-off, which applies to any data science, not just in medicine. And in medicine, we can recast the bias variance trade-off into what we call the relevance robustness trade-off. Essentially, relevance, patient relevance, is the opposite of bias. So if you have high relevance for a patient, then you have low bias for this patient. And essentially, it measures the trueness. It answers the question, is my inference true for my specific patient? And then we have the robustness, which is the opposite of variance, that statisticians are obviously very well aware of variance. When you have high robustness, you have low variance. And so the robustness or variance measures the degree of random error in our estimates, and it answers the questions, how close to each other are my estimates from a cohort of patients? This is very well known to many of you guys. I really like this. I saw this on a lecture, I think, by Martin Besmet, and I stole it. Shows a very beautiful example of this trade-off. We have here a bed that is very, very, very relevant for a specific person at a specific point in time, but it's not robust. We want things that also have robustness and can accommodate many different situations and many different people. That's why there is always a trade-off. So low bias by high variance here. And so we can see it in action. That explains, you know, that what we call the first law of data analysis, whereby we have, let's say, the underlying truth. Very often in statistical lingo, we used Greek letters. I'm originally from Greece, to annotate the parameters that are the real ones, like this one. But the real value of a parameter is always beyond our senses. That is why we have to model the truth and use capital, in theory, Latin letters or small letters when we have the values that we measure. And because we have a model of the truth, there will always be some distance. And some of it we know about it. In the machine learning world, we like to distinguish between the irreducible error that we don't even know about and the reducible one that we can even measure. And so that's the distance from the truth. And when we have the confidence intervals, we know that when we have, let's say, a small sample size, they're going to be, as measures of standard error, very wide. And because they're wide, they are more likely to include the truth. Everything else being equal, then if we increase the sample size, we will narrow our uncertainty estimates around our model. And this is why it will have lower chances of containing the truth. That's what we call now the big data paradox. That's what it is called. It was named this way by Xiaoli Meng. Some of you, I'm sure, know of him. He's a brilliant data scientist at Harvard. And he called it the big data paradox because of this was something that was seen with the 2016 election forecasting. We had tremendous amount of data to forecast the 2016 elections, and yet the forecasts were imperfect, in part because of that. And another situation, which I think is very relevant to a lot of us because it's very raw, we still remember the COVID pandemic, was this very beautiful paper in Nature with Xiaoli as one of the co-authors, where you see here the goal, the task was, when the COVID-19 vaccines were available, we had to forecast who is going to take it, how many people are going to actually take these vaccines, how many were willing to do that. And at the time, this Delphi Facebook survey of 250,000 individuals, not patients, was available. Largest public health data survey at the time ever in the US. Another survey, 75,000 people, and a much smaller one in just 1,000 people. And here you can see what actually happened. So the benchmark is the gray line with what actually happened. These were the forecast. And you can see that this very, very large one was consistently wrong. And exactly as described in the previous slides, the confidence intervals are very, very narrow because of the huge sample size. And so they're too small to even be visible because of the big data paradox. What happened was, as you can imagine, the Axios survey had less bias because the survey was more properly designed. It didn't have the various sampling biases that the others had. That's the trick. And so when you think in this way, you can understand that we can take advantage of it and reverse the narrative. And by reducing the bias in our inference, let's say for renal medullary carcinoma, even with small sample sizes, we can make a difference. And so what would be the perfect scenario of perfect robustness? Randomize everything. When you randomize everything, you don't need to think about potential confounders or any other aspects of the underlying causal network. Remember, in actuality, this will not balance the patients. It will randomization balances only in expectation if we run the same experiment an infinite number of times. But in the actual trial, it will not balance them. This is why we cannot randomize our clinical decisions. And as many of you know, the idea of randomization was first tested by Ronald Fisher in agriculture, but patients obviously are not plants. And many of you know that have run randomized trials that even in the ideal scenario where we can randomize the treatments, we don't randomly sample. We'll talk about that later. And even when patients get randomized, they don't stay compliant. There are all these issues that happen. So perfect robustness is impossible to achieve. And then the other extreme is perfect relevance when we know everything about our patient, their biology, their pathologic diagnosis, their environment, their goals and values, even the Krebs cycle. But that is also impossible. We can never know every single thing about our patient perfectly. That's why there's always a trade-off. There's no free lunch. And there is one extreme where we can achieve good robustness and relevance, those would be very deterministic inferences. Those have very, very, very high signal to noise ratios. That happen a lot with image recognition, pattern recognition like that. That's why you see deep learning approaches work so well in those scenarios. But in clinical medicine, we don't have this high signal to noise ratio. We have a lot of uncertainty. And so when we have large sample sizes and heterogeneous diseases like clear cell kidney cancer, then we want to go towards more robustness and we focus on big randomized phase 3 trials, etc. I made an arbitrary RCT boundary because it's a lecture that I give to kidney cancer physicians as well to help them design kidney cancer trials. And then you have renal medullary carcinoma that is a very, very rare, but also very, 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 very homogeneous disease. Uniformly deadly, very easy to know when a therapy is working or when it is not working, in which case you can capitalize on that relevance. And then there is some other cancers that papillary has a little bit more heterogeneity. We can focus on randomized trials. Chromophobe kidney cancer, on the other hand, has some more homogeneity. And as we learn more about these cancers, we can actually prioritize their relevance and reduce the need for randomization. This is what some of you know, the very theatrical Bayesian Edwin James. Many of us are fans of his great book, Probability Theory, The Logic of Science. This is why he said, when there is a randomized way of doing something, there is a non-randomized way that yields better results for the same data, but requires more thinking. That's essentially what we did for RMC. But again, there is no free lunch. Randomization is very, very, very valuable, very, very important to trial design. And I want us to take a minute here and distinguish between random sampling and random treatment assignment. I'm sure many of you know that random sampling is something that is done in a very different aspect of statistics, which is sampling theory. This is very different than experimental design that biopharmaceutical statisticians such as yourselves do. And when you do random sampling, which, by the way, is what could not happen with the vaccine uptake in the Nature slide, Nature paper slide that I showed you, that licenses the estimation of uncertainty estimates for group-specific parameters, whereas the random treatment assignment licenses the estimation of uncertainty estimates for comparative parameters. This is what we do in our clinical trials in medicine mainly. And what are the group-specific parameters? Things like, let's say, 18-month survival probability for one treatment arm, the median overall survival for one treatment arm, objective response rate, for one treatment or the control or whatever. Those are the group-specific parameters. Unless you have random sampling, when you estimate uncertainty estimates like confidence intervals for these parameters, you're making a whole lot of assumptions. You can still press the button and estimate them, but you have to know that you're making many assumptions. For the comparative parameters like hazard ratios, median survival difference, absolute risk reduction, that is what RCTs, the random treatment assignment, were developed. That's what we can more reliably, even if still imperfectly, estimate through standard RCTs. So essentially, RCTs are meant to be comparative. From a causal inference perspective, we can use, for example, the directed acyclic graphs from that causal inference school that heavily uses them. And you can see here that we have a treatment, we have to choose between a treatment versus control, and that can affect, let's say, our survival outcome in a trial. And when we don't have a randomized trial, then covariates like baseline variables can influence our choice of treatment versus control. So those are what we call confounders, and then random treatment assignment removes them. Remember, notice here, we don't need to randomly assign the treatment to remove this arrow. As long as we take away from the physicians and the patients the choice, this arrow is removed. So the value of random treatment assignment is not simply that it removes the confounding as it did here. The value, because you can do that without randomly assigning. This was, by the way, what Gauchet kept arguing with Fisher. And again, Gauchet, who many of you know invented the t-test, he admired Fisher immensely, but he thought that you don't need to randomize. But what Fisher would say is that the random treatment assignment does this magical thing where it allows the robust estimation of comparative parameters. This is what Fisher, and potentially even earlier in his PhD thesis written in Paul's name, and recognized. From a potential outcomes notation, another school of causal inference, you can see here this came from Neyman's PhD thesis and Donald Rubin in JASA, very, very nicely summarized in 2011. You can see here with the potential outcome rotations, the value of randomization is that you're able to estimate the difference between the observed sample means with the randomization. That's the beauty of it. But equally important is that you can estimate the variance of the difference. And remember, statistics is all about uncertainty. This is the key thing. This is what we need to focus more on. Not just point estimates of difference. They are secondary to the variance. That is the most important thing to estimate from randomized trials. And the beauty is how Neyman and Don Rubin explain how when we randomize the treatment assignment, we get a positively biased estimate of the true variance. The true variance is impossible to observe because we cannot see the potential outcomes for each unit. We cannot, go back in time and do it. But the positive bias means that our confidence intervals will be a little bit wider than they would be if they were not positively biased. We can narrow the confidence intervals if we make the units a little bit closer to each other, a more apples to apples comparison, by doing stratification and covariate adjustment. I know many of you are very, very well aware of it. But regardless, even if it is positively biased, the uncertainty estimates that we get from random treatment assignment are reliable. Now, another thing that we could do to remove that positive bias is just to assume that there is treatment effect homogeneity all across, which is easier across every unit, individual unit, which is easier to do if we covariate adjust or stratify. Another beautiful paper that I highly recommend explains how exactly the random treatment assignment essentially fixes the propensity score for a two-group randomized trial to 0.5. For those that are Bayesians from a hierarchical Bayes perspective, essentially you're putting a hyper prior of 1 to the prior probability of the treatment assignment of 0.5. That's very different from a 0.5 prior probability where you're putting the 0.5 because you don't know what's going to happen. Here, it's a fixed, it's an aleatory probability. It is not an epistemic probability. That's the beauty of random treatment assignment that Fisher and Neyman realized. Now, we wanted to see in practice how many people, how many trials, phase 3 RCTs in oncology actually make that distinction, how many present treatment group specific confidence intervals, which as I explained already, are less reliable. And we found that more than half of them do. And in fact, these treatment group specific confidence intervals that are not very reliable are increasing over time. Interestingly enough, many phase 3 RCTs are actually better conducted based on surveys that we've published in other manuscripts when they're done by industry. But this is one of the things that industry seems to be, for whatever reason, doing more than non-industry trials, presenting treatment group specific confidence intervals. Now, it's not the end of the world if you do that. And there's a beautiful paper in Statistics in Medicine by Msaouel explaining here that you can literally have the exact same mathematical regression model. And depending on your purpose, if you're using it for description, you can even use something that many statisticians, including myself, kind of frown upon, like using p-values for covariate selection if, you keep it in the model, if it's statistically significant. Depending on your purpose, as long as you understand why you're doing something, it's not the end of the world if you do it, as long as you understand it. Or then you can use literally the same equation for prediction or for explanation, causal descriptions as are done through randomized trials, which allows us to describe what is the causality, which treatment may cause better outcomes, it doesn't allow us necessarily to explain why a treatment is better than another. This is, the job of, let's say, my lab and the correlatives that we do, et cetera, et cetera. So not the end of the world if you give those confidence intervals, as long as you know why you're doing it. And it's important, again, to prioritize and to be very mindful of what is the purpose of RCTs, which is differences, which is to compare groups. And it helps, we published this in Harvard Data Science Review, where I essentially simulated data, from an RCT, and I said, have a big difference, between the treatment and control. The R code is in those manuscripts, and you can see here, you get one treatment that has a very, very significant difference than versus the control. But remember, the problem with these survival curves is that they focus on point estimates. We just talked and we said uncertainty is the important thing that statistics are meant to do. So point values, like shown in the Kaplan-Meier curves, are incomplete. They can actually be misleading. We need to focus on the uncertainty of the differences. And the beauty is there is a package made by Frank Harrell, the RMS package, that actually allows you to estimate this half-width 95% confidence bands that are positioned equidistant between each group's midpoints, ensuring that when this half-width confidence band intersect with one survival curve, they will also intersect with the other. And at the time points where they intersect, then the half-width bands will have mean that we have a p-value of more than 0.05 without multiplicity adjustment, of course, for the null hypothesis of no treatment group difference. So because here it does not intersect with the survival curves, without even knowing this, so forget that this exists, that I'm actually showing you the comparative metric, the hazard ratio and confidence intervals. Just by looking at the survival curve, you can tell that the p-value is less than 0.05. There is a so-called significant difference. So focus on the uncertainty for the comparisons. And you see it's a narrow uncertainty, does not overlap with the groups. That's how we can, just by looking at survival curve, we can make those inferences that there is a difference. Many people show instead the group-specific confidence intervals. Again, it's not the end of the world. You can still see that they're narrow, they don't intersect. You can extrapolate that there is a significant difference, but I would argue that it's just so much more cleaner to simply focus on the treatment difference. And here is another example. Here, I simulated the data and I said, there is no meaningful difference. Narrow confidence intervals around the null hypothesis of hazard ratio of around 1.2. And you can see here that the half-width confidence bands, they definitely intersect with the survival curves, but they're very narrow. So that means there is no clinically meaningful difference between the groups. Again, you can make that extrapolation by the standard way of showing the group-specific confidence intervals, but it's just a little bit more noisy. And here is a scenario where this is noise, okay? I literally asked R to just make some noise. And of course, if you don't look at the uncertainty and you just focus on the point estimates for the survival curves, you might start saying, oh, what is happening at the tail end of the curves? Maybe there is a signal for a difference. Again, remember, this is me literally specifying to make noise. And it's only when you focus on the uncertainty, which you can do either by visualizing it like here or by looking at the comparative metrics like hazard ratios, you can see that, there's a lot of uncertainty. There's very wide confidence bands. So this is noise. So again, you could see it also by showing the treatment group specific confidence bands. But again, it tends to be noisy. This is very important, guys, because this confuses people all the time. This is an example. I am not aware of a single clinician in any of the big oncology meetings that has understood what I'm literally going to tell you, okay? This is a phase 3 clinical trial, a big one that tested one treatment, this cabo-nivo-ipi, versus the control, placebo plus nivo-ipi, the backbone. And it included both this intermediate risk and the poor risk. This is a subgroup. They're just playing around with the Kaplan-Meier curves as subgroups, as clinicians often like to do. And they found a difference for the primary endpoint, and then they decided to look at the subgroups, and they found that in the intermediate risk, the cancers that are less aggressive, they're seeing this signal, and then they see this in the poor risk. Now, you guys are a little bit more savvy. If you look at the hazard ratios, you can see that they're very wide. They're compatible at the 95% level with a hazard ratio as low as 0.65, favoring the new treatment, and as high as 1.69, favoring the control. What conclusion can I make? Nothing. Why? Because this is essentially noise. You can even see it by the low number of events in here. In fact, clinicians, unfortunately, take this noisy estimate and they say, oh, this triplet therapy does not work as well in the poorest group. That is wrong. In fact, if you just take the poorest prognostic group as a prognostic factor, as a clinician, I have to make this decision, so I have to think about these things carefully. It is actually the poor risk, the more aggressive cancers that are more likely to benefit from early triplet therapy. Why? Because I may not get a second shot. You see what I'm saying? However, because of this confusion, because of not emphasizing the uncertainty for the comparative metrics, people are making these mistakes. And this happens all the time in oncology. We assessed, the subgroup analysis from forest plots from the annual meeting of the American Society of Clinical Oncology in 2020 and 2021, and they presented 99 forest plots, and only 24% contained even one or more subgroups that would show admit effect of heterogeneity. 57% only included noise, like you don't even need to look at them. You're not gaining any evidence. When I showed this to one of our statisticians and a very good friend of mine, Peter Thal, he said, this quote, if you take enough hikes in the forest, eventually you will get a glimpse of Bigfoot, which is the truth. So another thing, again, confuses people all the time. Literally, in the kidney cancer literature, only these two references will explain what I'm going to tell you, okay? And I think that you guys should be able to really understand this much more than my clinician colleagues, unfortunately. So we've had multiple phase 3 trials in kidney cancer in the adjuvant setting. Essentially, you do the surgery, you remove the kidney cancer, and now you want to give a systemic immunotherapy like nivolumab, atezolizumab, or even a combination immunotherapy or pembrolizumab versus placebo control, and see if you can reduce the chances that the kidney cancer is going to come back. That's the disease-free survival or recurrence-free survival, which is the primary endpoint of these trials. And you get one trial, Keynote 564, that ended up getting the FDA approval, and it is so-called positive. And then you get multiple other trials that are so-called negative. And clinicians look at the data from these trials and they say there is no difference when you give nivolumab based on this trial, Checkmate 914, but there is a difference when you give pembrolizumab. So they even are saying in many editorials and commentaries for these papers that, there is a mechanistic difference, let's say, between pembrolizumab and nivolumab. For those of you that know, these are literally the same drug. They target the same pathway. They're doing the same thing. But what is the thing you can see here? It's just that all of these trials are pointing in the same direction. In fact, when I meta-analyze them for you guys, you can see that there is a consistent effect. It's just a weak effect. This is, regression to the mean, exaggeration of the one trial being positive. That's why you're getting a strong effect size here. It's probably around here. It's a weak effect of immunotherapy. All of these trials point in the same direction. It's just that all the other ones are inconclusive. So clinicians will say, is there a difference between the drugs? Is there a difference between the duration of therapy? They're all about the same. Is there a difference between the inclusion criteria? There is a little bit. That can play a role because the inclusion criteria, if you include more aggressive cases, you get more events, you get more precision, you get more power. The important thing is, what are we seeing? More narrow confidence intervals with Keynote 564 because of increased design power. And this is not luck. If you look at this carefully, you will realize that this was by design by the company that did this trial versus the other companies. And we have the table here where you can see it. Okay, so in the adjuvant setting, you get much less events compared with the metastatic setting. In the metastatic setting, you're much more likely to progress quickly, et cetera, et cetera. So you need lower sample sizes in the metastatic setting to get events. And these are the equivalent trials. Keynote 426 used a similar kind of regimen as Keynote 564. And here we have Prosper versus Checkmate 025. You see the equivalent trials, and you see how Keynote 564 by design had more power. And the other ones did not. Interestingly enough, if you look, for example, here, this trial aimed for a lower sample size than the corresponding one in the metastatic setting. That is wrong. You need to actually aim for a higher sample size where you expect to see much less events. Same here, 900 versus 764. Same here. But this one is the only one that smartly makes sure to get a higher sample size versus the metastatic setting. That's why they have more power. The results make sense. You can see here, this is another evidence how much in the adjuvant setting you get much less events over time than in the metastatic setting here. Makes total sense, but for some reason, people don't get it. And now, having said that, and, made a little bit fun of clinicians, now, I'm going to be a little bit more pointed towards statisticians such as you guys. I'm sure at least some of you in the audience have advocated or designed what we call randomized non-comparative trials. And based on what I literally just told you about, that is an oxymoron, because the randomized trials are literally meant to be comparative. So it's an oxymoron, like invoking a true myth, like sharing an original copy or drawing a squared circle. And I started first encountering these designs a few years ago. I just was not aware that these things existed until I saw this paper in The Lancet. This is, one of the most prominent journals across medicine. And I'm interested in rare cancers, and we see in my department pheochromocytomas and paragangliomas. So I was very excited to look at the data of this. This was a randomized, placebo-controlled, double-blind trial for a rare cancer. I was super excited. So I look at its abstract, okay, and I see they highlight that it's the first randomized trial and etc. And I see they show the group-specific confidence intervals. I'm like, whatever, they can do that. And then I was looking, okay, where are the confidence intervals for the comparative metrics? And I couldn't find them. Like, what? And then I looked deeper and I found in the methods, that's the first time this is mentioned, that this was a non-comparative placebo-controlled trial. Nowhere in the abstract, nowhere in the title, that's the first time you see it. And I looked, this is the statistical analysis, and they say they did show comparative metrics for subgroups, which is far from ideal, but this was not a trial designed to compare the main effects, which is weird. Again, so you have subgroup comparisons. Some of you guys may frown upon that. Even for the QOL, they used changes from baseline for quality of life, and they randomized to a placebo, but without intention to compare. So the patients got placebo as opposed to the active drug, but not to compare. And so we wanted to raise awareness of this in the community. So we wrote this letter, and we wanted to understand. We really wanted to understand, where is this coming from? And we got, this reply that you guys can read from the group. And again, this came from statisticians. This is a trial designed by statisticians, etc. And you get these references they cite, and they say, these are ultra-rare cancers. I know about ultra-rare cancers, and they cannot do randomized trials. I agree. This is literally the first 15 minutes I spent to you guys saying, yeah, we cannot do randomized trials, but if we are going to do them, then they better be comparative. And so they cite this citation. So you can look at these citations and you can go, this is not relevant, or this one. But this one, if you go, it literally says that you need to compare if you randomize. Like it says randomization is a must-have. So literally in their reply was not fully coherent. So I wasn't very satisfied. Again, randomization being synonymous with comparisons. Why enroll a placebo arm? They enrolled 39 patients in the treatment arm and 39 in the control group. Why not enroll all 78 to the treatment arm and thus increase the accuracy of its estimates in the treatment arm, which, can be useful to do in the rare tumor? So all of these questions, and again, randomization is a quantitative method. It's not something that you just feel, and you're supposed to generate information. It's not something that just licenses you to say this is the first trial that, as they said here. No, you're supposed to do something with it. It's not just so that the paper has higher chances to go to a higher journal. So we wanted to understand how often this is, because to many theoretical statisticians, when we were discussing this, including some that write textbooks that many of us read, they were shocked. They couldn't believe that these things could even exist. So we found that there is at least 70 of them from 2002 to 2023. It's not easy to find all of them, so it might be more than that across medicine, because again, many of them don't say it in the title. Many of them, they don't even say it in the methods. You have to look at the actual trial protocol. So it's not a rare, quick, or a once-in-a-blue moon phenomenon, and it appears to be increasing over time. Thousands of patients have already been enrolled in these trials. Again, as long as we understand why they happen and we try to find potential benefits of doing it, which I'm having a hard time finding, it's okay. They do appear to happen mainly in oncology. So we wanted to raise awareness about this among statisticians. So Significance had actually asked me to write an article about the big data paradox. And I said, no, actually, there is this curious phenomenon of these randomized non-comparative trials that I think it's very important for the statisticians that read Significance to know. So they agreed, and so we published this, and they even asked me to write a table of how you can even spot them, because again, we had a hard time spotting these things. And so one of the things is, as we saw in the Lancet paper, you're not going to see a head-to-head comparison. You're going to see a randomized in the title, but you're not going to see it in the analysis. You're going to see essentially them doing two parallel single-arm analysis, and they're not going to have power calculations for between group differences. What they do is they do power calculations for each single arm, which is easier to do. You can justify, let's say, your sample size or whatever with that. And they would generally avoid comparisons. Those things keep getting published, okay? So the Journal of Clinical Oncology, the most prominent oncology journal, publishes such trials almost every month. And so we don't like to be nihilistic and just, complain, but we did want to raise awareness for this. So we sent a few letters that you can see here to say, hey, guys, this is something we need to take a little bit seriously. I know from friends and from my personal experience that there are at least some biostatisticians that do recommend them in oncology trial design workshops. And they say that you can do a randomized non-comparative trial where there is not enough resources like funding or patient numbers to meaningfully power a comparative RCD. But that sounds like, you want to have your randomized cake and eat it too. Like, why not just do a very well-designed single arm trial, or very, very carefully incorporate historical controls, etc., especially when you're giving to one group placebo. And so if you're going to do these things, and again, I'm trying to still man these ideas, I'm 100% sure that at least some of you guys in the audience have designed or even advocate these designs. And I'm curious to hear from you what you think, and from the many others that, think they're a bad idea. I've literally had statisticians call my clinic in shock that these designs exist. So I know there is many statisticians who are very opinionated against randomized non-comparative trials. So maybe, I'm trying to find any advantage. Maybe you can use randomization to control enrollment flow, accommodate logistical constraints in drug supply. But then if you do that, why not compare? Maybe you're doing it because you think you're not going to have enough power. Of course, you can increase your power if you have high resolution endpoints, etc. But let's say you're saying, I'm never going to have enough power to do the comparison. I want to compare in the future. And I want to keep the arms concurrent so that if new evidence emerges, we can reanalyze with direct comparisons. I can buy it, although I would argue that why not compare from the outset just with less strict criteria initially, and then do flexible interim analysis? It just sounds so much more natural to me, to the purpose of randomization. I would say why don't you prioritize modeling bias in external control comparisons, which I haven't seen really those RNCTs do any of that stuff. They, just do this and not care much. And, thankfully, because we sent these letters, one of the replies actually pointed to this very nice review, which is written by actual statisticians that are very good in their field. And they do advocate for this design. So that was actually my first time me seeing some people that actually know what they're talking about, advocate for this. I still did not find it convincing, but I think that at the very least, there's some people at least trying. They say that you can use, the treatment arm and the control arm to calibrate the results. And indeed, as expected, by doing the randomized non-comparative trials, you don't need to have the type of sample size that you will need for comparisons. But then when you calibrate, like, what do you mean by calibrate? They say look at promising or disappointing or outside result. But what do you do when you look? Like, that's a vague thing. Do we look at point estimates? Do we look at uncertainty intervals? Do we look at something else? Like, what does looking even mean? Like, we need in a statistical plan to have something concrete, quantitative, and rigorous. So these are points I'm making, and maybe there are counterpoints from the audience here, or maybe not. So in summary, the bigger the data, the more surely we can fool ourselves. That's the big data paradox. When interpreting data analysis results, always ask what are the underlying mechanisms that generate the data. And medical RCTs can validly estimate the uncertainty of comparative metrics such as hazard ratios. Medical RCTs typically cannot easily estimate the uncertainty of treatment group specific metrics. Beware of randomized non-comparative trials. Make sure as peer reviewers or when you design them that you understand their potential limitations. Thank you for your kind attention and for the invitation, and happy to answer any questions now or through email or through any means possible.
Thank you, Pavlos. So, is there any questions from the online audience?
Hi, Yutao. Thank you, Samuel, for the presentation. This is Zixing from Gilead and Kite. As a fellow alumni from MD Anderson, I'm really glad to have this opportunity to hear the insight from the clinician, the other side of the statistician. So I just have a minor question, since this is the question always surrounding our clinic development group. So usually we have the hazard ratio and p-value. So these two metrics is very critical for the survival analysis. They are integrated with each other. But if you have an opportunity to pick only one of them, so which one would be most favorite from clinician? Maybe the question for the Samuel. Thank you.
Yeah, no, brilliant question. And in fact, I have a reference that we wrote with Peter Thal and Juhi Lee on interpreting randomized trials. I wrote this after immediately after my daughter was born, and when Peter, in his usual brilliant and theatrical manner, read the original draft, he said, "My God, you're insane for writing something like this." So in one of those tables, I have, what we think is the answer. As we said, statistics is all about uncertainty. And obviously, you guys know that for clinicians, what is important is to have meaningful difference. What is clinically important is the most important thing. So that immediately tells you that the number one metric that we should be interested in, that doesn't mean that clinicians are looking at this, but if I think that they should, is the uncertainty for comparative metrics like hazard ratios. So to me, let's say the 95% confidence intervals for a hazard ratio or mean survival difference or etc., the confidence intervals is the most important, is the number one. Because if you have that one, if you think about it, you can extrapolate the point estimate and you can extrapolate the p-value. So even from that perspective, you know that hierarchically, the confidence bands, the uncertainty for the comparative metrics is the number one thing to show. And this is why I highlighted, how important those confidence intervals for comparative metrics are important to highlight in the abstracts. You don't have to, because we get so many randomized trials being published and we clinicians get bombarded. We don't need to look at confidence intervals that are treatment group specific from an actual randomized trial. The most in the abstract, you can show it if you want the results, but in the abstract, the high yield thing is uncertainty estimate for comparative metrics, starting from the primary endpoint and then to the secondary endpoints. That's my answer.
Yeah, thank you for great insight. And I also want to mention my former collaborator is Dr. Kanishakar Sekar, maybe your current.
He's a very, very close collaborator and dear friend from our pathology group, kidney cancer expert that has seen tremendous number of RMC cases, as you can imagine. Yes.
Yeah, we have a paper about the RCC. So please say hello for me. Thank you.
I will.
Thank you, Zixing, for your question. There is another question from the chat box, and particularly question about the motivation for these randomized non-comparative trials, maybe due to the pressure from the medical journals, because medical journals may think randomized trials is the gold standard approach to evaluate the treatment.
Yeah, I think so. There is definitely, that's my sense as well, that there is some truth to that. My one thing, though, is that the biostatisticians are supposed to know these things, that you guys are meant to be the gatekeepers. You see what I'm saying? And I think that what happens, again, I think that this is people, including the biostatisticians, trying to be helpful. They want to be helpful to their clinicians. The clinicians, want to have impactful research so that they can, keep building their portfolio. And they say, maybe we can use this approach to, for rare tumors or whatnot, not have to do comparative power calculations, do this and that. I think that this is a situation where biostatisticians, we may be getting a little bit too accommodating. I think we should push back from a biostatistical standpoint a little bit more. And if we don't push back, at the very least, and say never do them, at the very least, when we do decide to do them, be very, very, very deliberate and strict. Like we can calibrate potentially more formally. There is efforts, including by Ritau, on incorporating external controls, etc., much, much, much more formally. Those are things that I would like to see being developed more before we start, blasting the literature as is happening now with randomized non-comparative trials.
Thank you. So yeah, I have also one question. So Pavlos, as you work in rare disease, so as we all know, rare disease, so doing a randomized trial, in many cases scenarios, and so in the biostat field, so we developed some hybrid approach that means that we have some randomized trial, but we don't use like 1-to-1 randomization. Maybe, we consider a 2-to-1, but we also borrow data from historical studies. So how do you feel about this hybrid approach as a clinician?
You have to be careful, of course, because as you guys know very well, when you do a 2-to-1 randomization or a 3-to-1 randomization, you have a cost in power. There is no free lunch. And versus a 1-to-1 randomization. However, what you said, I think, is a key aspect. The cost is counteracted by the additional information, as you said, from external information. So if we very carefully assess the trade-offs, then I am definitely supportive. I do think that whenever we can get away with it, we should randomize to compare. Like that just helps in so many ways. There is no substitute when it comes to measuring uncertainty for randomization. It's just it's impossible for us to be, like Jane said, so super smart that can accommodate for anything. We can get close, but not that. So whenever we can randomize to compare, we should. There are a lot of situations, as we have done with RMC, where we cannot, and we've accommodated and we've moved the field forward very well with single arm, well-designed trials for a very, very homogeneous population. So it's up to us, physicians, scientists, to elucidate those biological biomarkers that allow us to have very homogeneous populations that behave similarly historically, so they can be used reliably as historical control. So with these types of integrations, I think that there is a lot of opportunities beyond the standard, randomized trial approach. Absolutely.
Thank you. So yeah, I think because of time, we have one last question. So I think Dr. Peter Dahl requests to speak. So Peter, can you unmute yourself if you have any questions or comment to make? So yeah, I think we cannot hear you. So yeah, possibly you are experiencing some technical issues. And I guess there is one last comment from the chat box. So still questioning about the motivation to do randomized non-comparative trials, especially in oncology trials. So yeah, the audience asks if you can provide more information about this in oncology.
Beyond what I said, no. And again, motivations are subjective. I don't think we should, start pointing fingers. I think that we should work together to try and improve the rigor of our designs, gatekeep, especially from the statistician side. We really, really rely on statisticians to gatekeep and make sure to keep us in check. Even though, as Rita and Peter know, I in theory can do just about any statistic myself, I intentionally do not get involved in the statistical analysis or even most of the design for my trials. And this is intentional because I don't want my own biases to influence things. I help, I provide the context. It's a lot of fun to work with our biostatistics group. But I think that there is a very, very important gatekeeping aspect that we rely on our biopharmaceutical statisticians to maintain and protect us and improve us.
Thank you so much. So because of time, we have to stop Q&As, and thank you for your attendance. And I want to highlight that today is Dr. Msaouel's clinic day. So thank you for taking the time to give us a very insightful talk. Thank you very much.
Thank you for having me.